Hello there, this is Ms. Page. In this lesson, we are going to learn how to graph exponential functions, both growth and decay, that have a base of e. And so first we're going to talk about what we mean by e. So e is an irrational number. So another similar irrational number that you already know about is pi. And pi we use a symbol for because it is an irrational number, meaning that we cannot write it as an exact decimal value or as a fraction. 3.14, remember, is an approximation of pi. And so pi is irrational. 3.14 is not exactly pi. Base e is the same type of number. It is irrational. And so in order to kind of talk about where e comes from, or one way that we can see or explain the number e is using a series. And in that series, we have what we call factorial. And factorial is a mathematical procedure. So like addition, subtraction, multiplication. And when we see the symbol with looks like a little exclamation point, and this is read n factorial, it means an n has to be a whole number. So 0, 1, 2, 3, 4, no negatives, no fractions, no decimals, no roots, no nothing like that. It means that we start with the number n and we multiply it times all of the other whole numbers down to the number 1. 0 factorial is a little special. It is defined as the number 1. Then 1 factorial would mean, all right, all we've got is a 1. 2 factorial would mean what we have is 2 times 1, which is 2. 3 factorial would mean that we have 3 times 2 times 1, which would be 6. So 4 factorial would mean we'd start at 4 and multiply it times 3 and 2 and 1, and that would give us 24. 5 factorial would mean we'd start at 5, multiply by all of the whole numbers down to 1, and that gives us, let's see, that's 20 and that's 6, so 120. And factorials show up in different types of expressions. So it is something that comes around here and there, not just with base e. But here, what we have is, in Math 1, you guys learned about sequences, lists of numbers that follow a particular pattern. A series is when we add all of those together. And you'll learn more about the Maclaurin series in calculus. But the Maclaurin series, which says that we are going to take and add together, starting with a k value of 0, and going all the way to a k value of infinity. So we're going to go forever. We're going to add up all of these ratios that equal 1 over k factorial. So we have 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial, and so on and so forth. If we calculate those factorials, we get what's shown here. 1 plus 1 plus a half plus a 6 plus a 1/24, and so on and so forth, and that goes forever. If we start using a calculator and to add all these numbers together, and we keep adding as many as we can, we'll never be able to finish it because it goes to infinity, but we can add a lot of them together. And what happens is that the sum, the answer, so this equals this decimal. And as we add more and more, we get closer and closer to the number that we call e. So the decimal approximation that we often use for e is 2.718. Some, as much as you can remember is good, but at least to that thousandths place with the 8, if you have to, say, okay, what is the decimal approximation for e, or what number is e about equal to? 2.718, 2818, 28, and although it looks like it might start repeating, it actually does not. As you can, if you keep going, you end up with different digits. If it did repeat, we'd actually have a rational number, and it's not. All right, so When we have to do a base E exponential function and look at its graph or determine if it's growth or decay, we do have to realize E is a number that's greater than 1. So that means that if we want a growth function, we use E with a positive x value. If, however, we want to do a decay, remember for decay, our base value is between 0 and 1. So it's less than 1, but still positive. But since E is greater than 1, that means we'll have to use a negative x value in our exponent to represent decay. And we talked about that structure with like our base 2 and our base 10, but here we have to do it that way. Horizontal asymptote will work exactly the same way. It is y equals k. And key points we're going to talk about in a minute, including the y-intercept and 0 when appropriate. Getting that in behavior, one end, because this is exponential, will go towards that horizontal asymptote. The other will either head to positive or negative infinity. All right, so we are first going to talk about how to make sure we can correctly identify whether we have growth or decay. You might be wondering, well, why does this matter? Well, it matters because we are going to use the same key points to transform for both growth and decay. Basically the same strategy that I shared with you for graphing decay, where I started with my powers of 2, and then to turn them into a powers of 1/2, which would be the decay situation, I did a y-axis reflection. So we need to know if we have growth or decay so that we know whether or not to graph a y-axis reflection. And we will do that if we have decay. So that's what I was pointing to earlier. E is always greater than 1. So if the x is positive, then we're dealing with a growth function, because e to the 1, that's my exponent on my x, would be greater than 1. Same thing here. We're looking at e as our base. Exponent of 1x tells me my base is e to the first power, which is greater than 1. So this is also growth. This one over here, I'm looking at e to the negative x, so that means it's a negative 1. So my base is e to the negative first power. That's 1 over e, which will be less than 1. You might be going, well, how do I know that? All right, number sense. If you take any number larger than 1 and you do its reciprocal, you will always get a number that is smaller than 1. So if I take 2, its reciprocal is 1/2. So 2 is larger than 1. 1/2 is smaller. If I take 3, which is larger than 1, its reciprocal is smaller. If I take 4, its reciprocal is smaller. Let's say I take maybe a mixed, like an improper fraction, a mixed number. Let's say we have like 7 2/3. Well, that would be 23/3. That's greater than 1. Its reciprocal would be 3 over 23. Any time the numerator is smaller than the denominator, that's a number that's smaller than 1. And so that's true for all. So if we know E, which is about 2.71828 and so on and so forth, is greater than 1, then when we divide by E, 1 divided by E must be smaller than 1. All right, so here's our parent function. And you can see it's our growth. All right, we're going to use the growth as our parent, and we are going to use primarily these 3 x values. We could use, the negatives, but they're harder to remember. But we should be able to know that e to the 0 power is 1. So we'll use 0, 1 is one of our key points. That e to the first power, that's that decimal approximation, is about 2.7. So we will use that as one of our key points for graphing. And we should know that e squared, which is 2.718 squared, is about 7.4. Okay, and so we'll use that as one of our key points for graphing the transformations. So we'll have those 3 points that we'll need to use to graph. All right, so let's take a look at this problem. We want to graph, we want to state the key features. So just like when we looked at these types of problems with rational bases, like a base of 2, a base of 1/2, a base of 10, a base of 1/10, same strategies are true. There is one thing that's been added here to identify whether this is growth or decay. So here we're looking at our base being e to the first power. Actually, I think I'll put that above. So for this part, my base is e to the first power, which is e, which is greater than 1. That means this is a growth function. For my domain, remember this is an exponential function, so it's a continuous function, meaning its domain will have to be the set of all real numbers. And my horizontal asymptote is y equals k, and my k value is still found after my power. So my k here is -2, so I have y equals -2 as my equation for my horizontal asymptote. So now, remember those points we're going to use for transforming. So we're going to use our 0, 1, our 1, and this is coming from e to the x. So this is my x, e to the 0 power is 1, e to the first power is e, so that's about 2.7 to the nearest 10th anyways. And if e is 2, that's e squared. Oh, we probably don't remember, but we can get it into our heads if we do enough of these problems, at least for now, about 7.4. You could, I suppose, also get a decent approximation if you took 2.7 and multiplied it times itself, but it does not exactly give you 7.4. So it's better to memorize 7.4. All right, so what are the transformations we're going to do? Well, because we have growth, we are not going to do a y-axis reflection. We do have an a value of 2. So there's no x-axis reflection because it's positive, but the absolute value of 2 being 2 and greater than 1 does tell me I have a vertical stretch, and the factor of my stretch is 2. Taking the opposite of this -2 gives me my h. So my h is a positive 2. So I know it's heading to the right 2 units. These points in blue are heading to the right 2 units after I stretch them. And then my k value of -2 tells me that I'm going to go down 2 also. All right. So remember here what I'm looking at with a vertical stretch by a factor of 2, that takes each of these y values and multiplies them by 2. So 1 times 2 is going to become 2. 2.7 times 2 is going to become 5.4. 7.4 times 2 is going to become 14.8. So depending on the size of your graph, our grid over here, we may or may not always be able to graph the transformation of 2, 7.4. So remember that our horizontal asymptote is y equals -2, and that we have no reflection over the x-axis, so all of our points will be above that line. So I'm going to put my x-axis here, change the color. And remember my points, which have x's of 0, 1, and 2, they're all going to move to the right 2 units. So that means 2 is going to be moved to 4. So I think I'll put my y-axis right around here. Put some numbers on here. All right, so I'm going to graph my asymptote, y equals -2, as dashed line. Now I'm going to transform my points. So here, 0, 1. So 0, 1 is going to stretch to 2, and then it is going to move right 2 and down 2. So it is now here at 2, 0, which is the 0 in this case, then because it's on the x-axis. All right, 1, 2.7, roughly right about there. It's going to stretch by a factor of 2. Like I said, 2.7 times 2 is 5.4, so it's just under the halfway. Then it moves right 2 and down 2 and ends up right around there. And then my 7.4, well, it's going to stretch to 14.8, and then it's going to move right 2 and down 2. That would be like taking the 14.8 and subtracting 2, which would be 12.8. And I can't, 12.8 is up here somewhere, so it's not going to fit in this particular graph. So I'll just use these 2 points and draw my curve with, I should be able to tell that my left end is the one that's heading towards that asymptote, and the right end is the one then that is heading up. If I could actually hit that point. There we go. So there's my graph of g of x. Reasonable graph by hand. All right, so now I'm going to finish up the range in the end behavior. So my range is my y's, so I can see all of my y's, my points, my y values for my points are above this y of -2 for the asymptote. So my range is the set of all y's such that y is greater than -2. And my interval would be from -2 to infinity. In behavior, on the left end, that's the one that's going towards the asymptote. So for the left, x goes to -infinity, and y is going towards the y of that asymptote, which is that -2. On the right end, which means our x is going to positive infinity, our g of x, which is our y's, is heading up, so it's going to positive infinity. All right, and keep in mind, we said we were graphing growth, and there's no reflection to change it, so notice that it is an increasing function. What's interesting is if you have an x-axis reflection, it will not look like an increasing function anymore. It will actually be decreasing. So don't mistakenly think that it's somehow graphed wrong, because if there's an x-axis reflection, increasing does become decreasing because it ends up going, like that. All right. Another example here. Again, we want to be careful about the structure here. So that negative in front of that e, that's similar to like a negative in front of 2 that we've seen earlier. That does not mean negative e to the power, because remember, our bases have to be positive numbers. It means -1 times this power of e. Also remember that the structure to get the correct h means that we need x to be positive 1. And so we have to factor out a -1 here, and that gives us a +3, and then a +1. So when we see the given g of x equation, we have to interpret it correctly, which includes that first number, realizing that's -1, that's our a value, and that we have to, in the exponent, have to factor out -1. So we realize our h is going to be the opposite of 3. So our a is -1. Our h is -3, opposite of the +3, and our k is +1, still at the end. So that means our horizontal asymptote is y equals 1. We know that our domain is the set of all real numbers. So we can take care of those things right away if we want to. Remember this portion right here, exponential growth or decay, we have to circle one of those. So we have to realize that our base is this right here, e to the power of -1. That's 1 over e. And as we discussed, that must be less than 1. Since e is larger than 1, 1 divided by that bigger number is going to be smaller than 1. So that means that we have decay. All right, because we have decay, we're going to want to do a y-axis reflection. We are also, because a is negative, going to have to do an x-axis reflection. And then our h of -3 says we're going to the left 3, and our k of 1 says all of our points will go up 1. So what were those points again? We want to use x's of 0, 1, and 2. And remember, the y's correspond to e to the power of x. E to the 0 is 1. E to the first is about 2.7. E squared is about 7.4. You're probably already starting to know them. All right, so now I'm looking at deciding on my graph. So when I do a y-axis reflection, that's going to change x into a negative. Did you catch that? The y-axis reflection, which flips left to right, that changes x's to their opposites. The x-axis reflection changes the y's to their opposite because it's an up-down reflection. And then we go left 3 and up 1. So because of the x-axis reflection, that's the one that tells us all of our points are going to be below the horizontal asymptote of y equals 1. So I'm going to put my x-axis way up here, and then this line will be my y equals 1. So this is my asymptote. Then my y-axis, well, I'm going left 3. So that means that 0, we have x of 0 is going to move left 3 to negative 3. But it's also going to have a y-axis reflection, which means it's going to flip and we'll end up with, well, actually, no, zeros, because we'll do that y-axis reflection first. Okay, because we do the y-axis reflection first before we move left, what's going to happen is that 0 will stay 0, then it'll move left to negative 3. 2 is going to reflect across the y-axis to negative 2, and then move left 3 to negative 5. So I need to make sure I can get to negative 5. So I'm going to put my y-axis over here. There'll be plenty of room then. And that's one of those things that becomes easier the more you think about how these transformations are moving your points. So now I'm going to put some numbers on here. This helps my eyes make sure I graph things in the correct spots. All right, so now let's take those points. So 0, 1, 0, 1, I'm going to do the x-axis reflection first because that'll move my points onto my grid and then I can do everything else. So 0, 1 is going to reflect down here. The y-axis reflection will leave it alone. It will then move left 3, 1, 2, 3, and up 1, and up right there, which is also the 0 of negative 3. All right, and then I have 1, 2.7 is going to flip down to 1, negative 2.7, which is roughly right about here. Then it's going to flip across the y-axis. So now it's on the left side. And now it is going to move left 3, 1, 2, 3, and up 1. So it ends up right around in there. All right, 27.4. So the 27.4 is going to flip down to negative 7.4. Then it's going to flip from the right side of the y-axis to the left side. Then it's going to move left 3 units, 1, 2, 3, and up 1, and end up roughly right around there. So that means that it's my right end that's heading towards that asymptote this time, because the rightmost point is closer to the asymptote. And then the left end is going to keep heading down. So my range then, I can see the points here all have y's that are below my y value of 1 for my asymptote. So my range is the set of all y's such that y is less than 1. Be careful again with your interval notation. Remember, least to greatest for y goes bottom to top. So that means from negative infinity to 1. And our end behavior, our left end, which is the one heading down, the left means our x's are going to negative infinity. And since that end is heading down, our y or g of x function values are going to negative infinity. For our right end, that means our x is going to positive infinity, and that end is heading towards the asymptote, which has a y value of 1. So our y function values are going to 1. And that finishes up that problem. So remember we had decay, and in general, a decay function is a decreasing function. This one is definitely not decreasing. Don't let that bother you, because remember that x-axis reflection, that x-axis reflection we had to do because a was negative 1, changes that decreasing feature into an increasing feature. So this perfectly makes sense. We had decay, which means it started as decreasing. The x-axis reflection changed that to increasing. All right. Here's a practice problem. I encourage you and recommend that you pause the video here and try this one, and then come back and we'll take a look at this one in a moment. All right, let's take a look. All right, so this one is a growth. Your base is e to the first power, which is of course e, which is greater than 1. So you get growth, domain, that's set of all real numbers just like before. Your k value is -3, so you got y equals -3 as your asymptote. And then it shows a little bit more than what we were transforming, but we've got our transformations are a left 1 and a down 3, looks like. No stretches, no reflections to do, nothing like that. So it just took 0, 1 and moved it left 1, down 3. So this is 0, 1. This would be your 1, 2.7 approximately. So 1, 2.7 moved left 1, down 3. And this is your 1, 7.2 right here. All right. Another practice problem. Again, I encourage you to pause the video, do this one, and then come back to check. All right, let's take a look at the results for this one. So this one's decay, and it's because of the e to the negative first power there, which would be 1 over e, which would be less than 1. Hopefully you realized you had to factor out that -1, giving you an x minus 4 in parentheses. Otherwise, you would have gone to the left instead of the direction you should have gone, which is 4 units to the right. Here our k value is 0, which means that our horizontal asymptote is y equals 0, which remember is the x-axis. And so you can see how our curve is approaching the x-axis here. And our other transformations, our a value of 1/2 means that we have a vertical compression by a factor of 1/2. And then our h value of 4 gives us, like I said, that 4 right. And because we have decay, that means we're also going to need to do that y-axis reflection. So 0, 1 would, and you can do the compression or the y-axis reflection. Well, do the compression and the reflection. You could do, actually, you can do, yeah, either order, doesn't matter. So what you're looking at, yeah. So here I'm looking at 0, 1. I can compress it, stays where it is, and then moves 4 to the right. So this is your 0, 1 point. Your 1, 2.7 compresses to half of 2.7. So taking 2.7 and dividing it by 2 gives you about 1.3, 1.4. So that compressed to right about here, and then it moved right. So 1, 2 points. Oh, I forgot my y-axis reflection. So it compressed right about there. Then it flipped to the other side, and then it moved right 4. 1, 2, 3, 4, which put it right there. That 7.4 compresses by a factor of 1/2. So we've got about 3.7. So 7.4 compresses to 3.7, and then it flips to the left, and then it moves back 4 and puts it right back in that spot. So all of our points have y values for range above the y value of our asymptote. So that's why our range is y is greater than 0 and our end behavior as shown. All right, let's do our closure here. So using the graph, what is the value of k for this function? What is our k? All right, if you decided that your k is 4, well done. Your k value here, it must be 4, because remember, k corresponds to the number for our asymptote, and our asymptote is y equals 4. So that tells us k must be 4. All right, so that brings us to the end of this lesson. I hope you have a wonderful day.